Hello, my name is Jolina Eger, and this is my Physics 2 Lab 3 circuits. So for an introduction, we'll go over experimental goals, key findings, relevant background, and some predictive calculations. The purpose of this lab is to predict the circuit behavior with both parallel and series resistors, measure both current and potential, and then explore the behavior of resistors and capacitors. This is going to be done using the circuit construction kit available by Colorado PHYS. So the key findings were that we verified the node and loop rule, and that we found current in an RC circuit is time dependent. So the relevant background we need before we get into the lab are understanding both the node and loop rule, which the node rule says that for the conservation of charge, the current flowing in and out of a node must be equal. The loop rule states that the sum of all the voltage drops around a loop is going to be 0. And then Ohm's law relates the current, voltage, and resistance by V equals IR, and this equation can be manipulated to isolate these variables. So in this lab, the system is going to be the circuit, and the surroundings are going to be everything else. We were able to find the current flowing through this circuit theoretically using Ohm's law, and that value is found to be 0.02 amps. Methodology-wise, we'll be using the Colorado PHYS circuit kit and then some graphing in Excel. So the experimental procedure will kind of first start with 2 ammeters, and then we'll reverse one of the ammeter's connections, and then we'll have an ammeter and a voltmeter, and then we'll move into the RC circuit component portion. So results and discussion. So we first built the circuit that we predicted the current for earlier and found that the value aligned with the calculated value. And then we reversed one of the ammeter's connection, but that doesn't yield any changes to the circuit since the current flows the same through either end of the ammeter. And then adding a voltmeter into the circuit, the ammeter now reads 0 since the voltmeter in the circuit kit is considered to be an ideal voltmeter, meaning it has a super high resistance, and the voltmeter reads 3 volts since there's no other voltage drops present in the circuit. So then we were asked to calculate the voltage drop of the components throughout the circuit, which could be done using a loop rule, which again states that the voltage drop around the loop is going to equal 0. So we can first have the voltage drop across the source, and then the 2 resistors, noting that the ammeter has no voltage drop across it. So here is the visualization of how that voltage drop changes throughout the circuit, and it can be seen that the initial and starting point are both 0, meaning that the change in voltage was 0. However, no change is seen when the ammeter is added since the voltmeter has an extremely high resistance, meaning that little current flows through it. So this just validates what we were able to verbally state before. So then when we substitute the ammeter that was originally at the top of the circuit to be in parallel with the 100 ohm resistor, the ammeter has a lower resistance, which means that the current will now flow through the ammeter as opposed to the 100 ohm resistor, which essentially negates it from the circuit. So that changes the new current value to be 0.06 amps without that 100 ohm resistance component. So then we were asked to calculate the resistance of each element in the circuit, which can again be done using Ohm's law, which will manipulate to be R equals V over I. And so then it was found that for the 47 ohm resistor, the resistance would be 48, and for the 100 ohm resistance, that would be 102, with the wire and the ammeter having 0 resistance. This is due to just some rounding error. Those values are close to the values that we know the resistance is, so it's works out. So now moving into the RC component of the lab, we were able to simulate both a charging and discharging circuit, where it took the 10 ohm resistor 10 seconds to charge and discharge, and the 20 ohm resistor 20 seconds to charge and discharge. So then analyzing the circuit further, the circuit was a 9-volt battery, a 200 microfarad capacitor, and a 30 ohm resistor that were all connected in series. So taking the time and voltage and then relating those two linearly through the log of the voltage over the initial voltage, we were able to graph this linear trend line here, where theoretically our RC value is found to be 6, multiplying the resistance and capacitance values respectively, but experimentally, when we take the inverse of the slope of the line that we plotted here, we find a RC value of about 6.9. So there were some potential sources of error during this lab, one of them being difficulty getting exact measurements with like timing and things, another being that the ideal online circuit components aren't one-to-one with real behavior, and then there were some rounding errors affecting our calculations earlier. So to summarize the key findings again, we were able to verify both the node and loop rule is true, and then understand that current in RC circuits is time dependent. So then what if we were doing this experiment in real life using an actual ammeter instead of an ideal one? The actual ammeter would have a resistance value, thus affecting the current. And then what if we did this experiment with a real battery and then we had no resistor in the circuit? Well, without a resistor, we wouldn't find any hindrance to the capacitor being charged, so it would charge instantly. However, since batteries have an internal resistance, we still wouldn't see this immediate charging. Thank you.